Okay, for something to be continuous, we need to know three things. One, that the function exists at that point, that the limit exists as you approach that point, and then to make it continuous, both the limit and the function at that value need to be equal or the same. So in other words, the function exists at a point, the limit exists at the point, and the functional value equals the limit. If these are not true, then we know that it is discontinuous at x equals a. So here's an example. Determine any points of discontinuity that we see. So on A, we're looking where do the function and the limit not equal each other. One value we can see on this first example A is that at x equals 0, it would not be continuous, even though the limit exists there. And even though we have a point, they're not equal to each other, and so it'd be discontinuous at x equals 0. Another place this one would fail to be continuous would be at x equals 1, and the reason here is that the limit does not exist. As you approach from the left, it equals 0. As you approach from the right, it's some other value. They're not the same, and so it would not be continuous there. B, where is this one discontinuous? This would be discontinuous at any points where you don't have a value. And in this case, there would be two of them at x equals 1, because 1 here would make us have division by 0. And so that one, it's discontinuous also at x equals -2 for the same reason, because -2 gives us division by 0. Those points are not in the domain, and so they can't be continuous there. In G, or for this g of x function, in number C, it'd be easiest if we did a little factoring, so we can do kind of like we did in B to figure it out. So if we factor out this x, now we can see the two places that this would be discontinuous. One would definitely be x equals -3 for the same reason as the problem above. Now also here, this point at x equals 0 would also be discontinuous. Now, even though it cancels out here, that would be a hole in the graph, and it would not be continuous there. So even though the limit exists there, we don't have a point, and so it would not be continuous. All right, example 2, determine any points of discontinuity. We have a piecewise function here. So for part A, it says show that f is discontinuous at x equals 3. Justify by checking each of the three conditions above. So the first one, does the point exist here? Yeah, f at 3 is equal to 4, as we can see right here. 2, does the limit exist? Yeah, the limit here, as x goes to 3, we would actually follow this function, since it's that function everywhere except right at 3. So what would we get if we evaluated this limit here? I think we're going to have to do some factoring in order to figure out this limit. So I'm going to factor the top into difference of squares. Now these would cancel, leaving us with 3 plus 3 or 6. So the limit does exist. This is approaching 6. The problem here is these two values are not matching up, and so it is discontinuous because f of 3 is not equal to the limit as x approaches 3 for this function, and so it's discontinuous. How should f of 3 be defined to make this continuous? If we wanted to make this discontinuous, instead of having this equal 4, we would want it to be 6, so that f of 3 would be 6, and then it would match our results of our limit. Okay, last one, give examples. of each. So give an example of a function with a removable discontinuity, a hole. Well, we had one of these before. If you have a hole, that means the limit exists there, but it's not defined at that one. So one of these rational functions would work, something like with a numerator and denominator, and if it's not going to exist at 2, that means here we'd want x minus 2. So that means it's not going to define there. For it to be a whole, we should have that same value on the top with something else there, like we could throw another x in there. That way it's going to have a limit as we approach 2, but not be defined there, and so it would be a removable discontinuity. Give an example of a function with a jump continuity. We can look back at one of those examples we did earlier. Here was an example of a jump, and so if we define this with maybe some kind of piecewise function, we could definitely do that. Something like this, where on one side of x equals 2, we could maybe just use our function x again. Let's say that's when x is bigger than 2, but then when it's less than or equal to 2, because that's where we're looking at, we have some other function that would give a different value, so maybe like 5x plus 1. So if you put 2 in both of these, you don't get the same thing because there's a jump there.